I have a video here constructing the Wonder Hoover Dam Secrets Review. Let's see the secrets that the Hoover Dam has to reveal.
The galleries located inside the Hoover Dam are pretty amazing. They are responsible for draining water from beneath the dam body. However, if these simple-looking galleries were absent, there would be devastating consequences for the dam. To better understand the clever engineering behind the Hoover Dam, let's first explore how they placed the concrete in this dam. Did you notice the strange choice made by the Hoover Dam design engineer, Mr. John Savage, at the end of this stylish block-by-block concreting? He left a 6-foot wide gap in the center of the dam. Why exactly did he leave this gap? If they hadn't left this gap and constructed as shown, the dam body would have formed cracks within only 1 to 2 weeks of concreting. This is because concrete contracts.
Yes, that is true, and the same reason why big dams like this are built block by block. It's because of the temperatures which are released during the curing of concrete. The process of concrete curing is an exothermic reaction, meaning that there's a lot of heat which is released, and due to the hydration of cement, the water will be released as well, meaning that the volume will reduce. And if you don't leave an expansion gap like this, that heat will cause stresses in the structure and that will lead to cracking. It's the same concept that happens when you have a ceramic container or a glass and you pour boiling water in it, then instantly you pour cold water, like really cold water, it will crack. It's the same concept because there's like a stress gradient that happens which causes a lot of stresses that will cause cracking because concrete is inelastic for the most part and it cannot handle expansion of that nature.
Or wants to reduce its length when curing. However, the length reduction is not possible since the ends of the concrete blocks are trapped by the mountain rock. This will induce a strong tensile stress in the concrete, causing the dam's body to crack. When you place a gap in the center, the concrete is free to contract during the curing. This way, no stress is induced in the concrete. Once the concrete had cured, the engineers filled this gap with special grade concrete. Isn't this such a genius construction idea? Wait a minute. The site where the construction is taking place was originally occupied by the violent Colorado River. When the river flows like this, it's clearly...
Yeah, I don't know what the snake is doing in there. We don't have snakes on construction sites. I think it's there for dramatic effects.
Possible to undertake any construction activity safely or successfully. So how then did the American engineers tame the Colorado River and dry the land to be able to build the dam? Their only option was to divert the...
Yes, even before going to the construction process, there's a phase which is called siting. It's part of the pre-planning of dam construction. You have to find an appropriate site to construct the dam. And usually there's some considerations like the geological formation of the area, how strong the rock is at the site that you want to construct the dam, and depending with the type of dam that you want to construct. And in this case, the Hoover Dam is a double arch dam, and double arch dams are usually constructed in steep gradient slopes or gorges.
River. If you divert the river like this, you can begin construction in the dry area. The river will flow unaffected after the diversion. Although this is a great idea, diverting such a violent and massive river comes with its own challenges. A practical solution to divert the river is to build 4 such giant tunnels around the construction site. After the diversion tunnel construction, you can build temporary dams called cofferdams. Now the water can only flow through the tunnels. Since the tunnels are huge, they won't disrupt the original river flow in any way.
And this is actually a good strategy as well, because you can then afterwards utilize those tunnels in the case this dam's purpose is for hydroelectricity generation. You then use those tunnels and connect them with the turbines and generate electricity.
Look at this strange machine called a jumbo drill. American engineers invented this machine just to do the construction work of the diversion tunnels. Those days, tunnel boring machines were unpopular at the time. The only option available to the engineers was controlled explosion using dynamite. The jumbo drill could accommodate almost 30 drills at a time. They created holes for the dynamite powder on the rocks. These drills were operated by compressed air. Pretty interesting, right? After filling the dynamite, the jumbo drill and workers were moved away to safe distances. Electrically controlled explosion of the dynamite was the next step. Now, it's shovels' turn to enter the site. They meticulously cleared the debris away. Rather than throwing the broken stones away, we will see a little later on what they did with them. The workers won't be able to resume their work right after the cleaning operation because of these dangerous hanging rocks. Next, they had to concrete the tunnel to secure the rock. Concreting of the bottom portion was relatively easy. However, this method won't work for the remaining portion of the tunnel. The workers first placed reinforcement bars as shown. They bonded the reinforcement bars with the rock by spraying concrete in it. Now comes an interesting machine, an expandable form machine. This hydraulically powered machine was able to expand after entering the tunnel.
Yeah, this method of tunneling is still practiced. If you're going through hard rock, this is the most favorable tunneling method used. When you're in soft soils, obviously it's better just to use a tunnel boring machine, because tunnel boring machines are really sophisticated. They're designed in a way that they use compressed air to balance the surrounding soil so that it doesn't collapse inside.
Side concreting was accomplished this way. Concreting the remaining top region was done using pneumatic concrete guns. After concreting was completed, the form machine was removed. Now it's time for the jumbo drill to go further inside. This cycle was repeated multiple times, and after 18 months of seriously hard work, all 4 diversion tunnels were ready. They opened the diversion tunnels by removing the soil in front of them. A small stream of river water could enter the tunnel. Here's a thought-provoking question. What do you think will happen if the trucks start dumping rocks and soil upstream of these tunnels? The water level will obviously rise. The trucks are increasing the height of this rock mountain. Because it's now taller than the top point of the tunnel, the water in the river must be diverted completely. Hooray! We've successfully achieved a perfect river diversion and dried the construction site. The rock mountain we just built is known as a cofferdam. The same broken stones they cleared during the tunnel construction were used in construction of the cofferdam. The diverted water in the tunnel occupies its original riverbed after approximately 900 meters. At the other end, another cofferdam is constructed to prevent any chance of water entering the construction site. Should we undertake a massive concreting operation on this dry land to build a dam? You can construct it, but when the dam fills with water, it will just topple over due to the strong hydrostatic pressure. For the dam to remain stable, it needs strong support from all 3 sides. Here's how they introduced a strong support for the end of the dam. First, remove all the weathered and weak rocks. Now, cut both the mountains to fit the exact shape and size of the dam body. To accomplish this, the workers again used dynamite explosions and jackhammers.
Yes, this is one of the most important stages of dam construction, making sure that the foundations are properly made and the dam is anchored in highly competent rock. And not only the weathering of the rock, you have to consider the joints in the rock as well, because if you construct a dam in a rock formation which is highly fractured, it means that you lose a lot of water and there will be no point of constructing a dam, because the idea behind constructing a dam is to have a reservoir of water. So this is a really important phase of dam construction. Let's say if there's a problem with your foundations, it's really difficult to fix foundations because they're usually buried. It's either underneath the dam or on the sides of the abutments, which is different from if there are some cracks or some sulfate attacks on the dam structure itself. Yeah, you can come up with some solutions to fix the dam structure, like using grouting to fix those cracks, which is different from the foundations.
For the bottom side of the dam, workers also removed all the weak rock and reached a solid section called hard strata. To reach the hard strata, they had to dig until a whopping 300 feet down. Now, the site is ready for the massive concreting operation and main construction activity of Hoover Dam. They did the concreting block by block. The advantage of such a concreting method is clear. The heat generated can be dissipated easily. Moreover, they made room for cooling water pipes inside these blocks. Once the blocks were solidified, they filled them with concrete slurry. The asymmetry in the block arrangement ensured that they'd form a strong connection with one another. When the concreting was completed, the top section had sufficient width to accommodate a road. Please have a look at the dumping mechanism Hoover Dam engineers invented to do fast concreting. Initially, they kept the concrete bucket on the floor. Now, one worker removes the pawl lock. At this stage, if you pull the bucket up, the half-split hinged bottom will open automatically, dumping the concrete down. Let's close the diversion tunnel and remove the cofferdams. This is a magnificent view. The water level in this dam is gradually rising. However, our current dam design may fail when faced with this massive body of water. Let's do an experiment to understand why.
That's why a double arch dam is thicker at the bottom and slim at the top. The reason being, a triangular shape has better stability than a square shape. If it's thicker at the bottom, it lowers the center of gravity. When the water pressure is applied on the other side, it won't flip over.
This dam stands strong within the soil. Now let's introduce water and see what happens. Is a muddy water. Anyway, when I release my hand, the dam just lifts up.
This is the other reason why the rock formation on the construction site should not have a lot of joints and folds, because if the water penetrates, there's an uplift pressure which is exerted on the dam. Water is a lot of pressure and it's incompressible, so it means that it has to go somewhere. It's not going to reduce in volume. It will end up compromising the foundation and the dam itself, either by erosion or piping underneath the dam, which will in turn result in the destabilization of the dam structure.
This is because the seepage water which flows below the dam exerts an upward force. This is known as uplift force, and uplift causes a huge instability to the dam.
This is why they gave provision for the drainage or inspection galleries during concreting of the dam. How can they reduce uplift force? That's the duty of these drainage holes. These grout-filled holes suck seepage water from the dam's foundation and greatly relieve the uplift pressure. The collected water is eventually pumped out downstream. These galleries are also used for inspection. It's amazing to know how such simple technologies provide great stability to the dam. Now we've reached the most crucial part of this video.
Yes, and all these technologies as well, they came about from learning from our previous mistakes. Prior to the construction of the Hoover Dam, there were previous dam structures which had collapsed. Back in the days, we didn't have as much understanding about how water behaves and the resulting cause of those disasters, which only came about after accidents of this nature happened, and then back analyzing and back calculating and then realizing that uplift pressure in most cases is relatively high enough to destabilize the dam structure.
Video explaining how electric power is generated by the Hoover Dam. These workers are building the power generation facility of the dam in this U-shaped structure. Gigantic Francis turbines and generators would sit in this location. Hoover Dam's power production capability is massive. There are 17 turbines and generators arranged in this U-shaped power production facility. The Hoover Dam uses a type of turbine called a Francis turbine. Water initially travels via this spiral casing, and finally through the runner blades. The force of the water turns the runner. The runner is
In my opinion, this is the beauty of hydropower, because the electricity is generated through mechanical means. It's just the water head coming from the top and flowing downwards and just using its water kinetic energy to rotate the turbines. And from that process, electricity is generated, which is better than using fossil fuels like coal.
directly connected to the generator. If you observe the generator, you'll see that both the rotor and the stator are just copper coils. No permanent magnets are used here. However, the rotor needs a supply of electricity to generate magnetic fields. This current is supplied by an exciter, which uses a permanent magnet stator. Now it's time to transmit this electric power. But first, notice the size of this scroll case. How can such giant turbines and generators be installed inside this power generating facility? If you've ever visited the magnificent Hoover Dam, you might have noticed a weird-looking tower and pulley cable arrangement. This beautiful machine, a cableway, did the impossible task of installing turbines and generators. You can see that all these main wheels are connected via a carriage. These tiny support wheels and support wires prevent them from falling down. These two drums make this arrangement move left or right thanks to simple cable pulling. The ends of these cables are attached to the carriage. This animation shows how it's moved left. Movement to the right is achieved in the opposite way. Let's discuss the hoisting mechanism. An additional drum was used for this purpose. You can see the clever passage of the cable around the pulleys. You can also predict what happens to the hoist when the drum rotates. The 3 cable drums we just saw are kept inside a hoist house. This is how workers transported material to the turbine region, and this hoist mechanism is still used today. Sheer genius, right? After the transportation, a large gantry crane was used to help assemble and install the generators, rotor, stator, and other heavy components. The last question that remains is, how does the water from the reservoir reach the turbine? That's the duty of these intake towers. Here's an aerial view. Now we need to connect the water collected at the intake towers to the turbines downstream. Can you tell me an easy solution for this? Yes, the diversion tunnels are of no use once the dam construction is over. Just connect a small piece of pipe from the intake tower to the inner diversion tunnels. The water will flow downstream. From there, extend a few tunnel branches to the turbines. However, for the other 2 intake towers, they had to construct new penstocks. Let's follow a few water molecules starting from the intake towers to the turbine to understand penstock geometry more clearly. Unlike the diversion tunnels, the penstock needed steel lining. Otherwise, over time, the tunnel would erode due to...
Yes, it's either the tunnels will collapse through erosion, or there's a concept in hydraulics called the hammer. It all boils down to the force that is exerted by water and the incompressibility nature of water as well. The forces which are generated, they can only be equal and opposite. The pressure which is exerted due to that pressure differential from the top of the intakes to the bottom of the fall is so huge that the material used for the tunnel should be strong enough to resist that force. And in most cases, the tunnels are lined by high carbon steel. I don't know how they did it on the Hoover Dam. It's only one way to find out.
Otherwise, over time, the tunnel would erode due to the water force. To construct the steel lining for the penstock, a specialized fabrication plant was set up near the dam site. The penstocks were made from steel plates, rolled using a giant press. 3 such plates were welded to form large pipes. Using the same cableway, the penstock sections and other large components were lowered into the dam's tunnels. Specially designed trailers waiting at the access tunnels carried them inside the tunnels, where the pieces were finally connected. Pressure pins were used to form a continuous connection between the intake tower and the turbines and outlet valves. We've seen the use and construction of the penstocks in the Hoover Dam. However, why are these workers working on another tunnel near the dam? This is known as a spillway. Suppose there's no spillway for the Hoover Dam. If the water storage breaches the height of the dam, it will overflow. This is obviously a dangerous situation. Such water overflow can completely destroy the facilities at the downstream side. This is why spillways are used. The spillway tunnels are located 27 feet below the top of the dam. Hoover Dam spillways have an interesting rotating mechanism. If the dam authorities feel that the water level increase may subside soon, they will rotate this structure. This allows the dam to hold even more water. If the water level increases further, the water will overflow above the structure and, via the spillways, it will be discharged downstream. Let's observe the dam once again from the top view. Can you identify an easy way to construct the spillway? Yes. Just make use of the downstream portion of the big diversion tunnel. Hoover Dam engineers were smart, right? After 5 years of tedious planning and construction activities, the dam was finally ready to store the water. Removal of the cofferdam was a tricky operation. They first made controlled openings in the cofferdam, allowing the river to erode so they could remove the temporary structure. In some specific sections where water erosion wasn't effective enough, a small blast with dynamite was used to break the cofferdam material. Finally, in August 1935, the cofferdams were removed and water started rising in Hoover Dam. The violent Colorado River was finally tamed by the Great Hoover Dam. 1 month later, when the dedication ceremony was held, the public was awed by the mesmerizing view of the massive water storage. The power production capabilities of the Hoover Dam were not yet in effect at the time of the dedication ceremony. They installed the first generator about a year later, in October 1936. However, it was only in 1961 that the Hoover Dam's entire power production potential was achieved,
producing an impressive power output of 2080 megawatt. But today solar power plants are able to generate the same amount of power output, 2000 megawatt. If you would like to learn how to design a photovoltaic power plant, please check out my course on the same.
Yeah, this was a great video. It's always interesting to see how these huge infrastructures are constructed. And in this case, it's a dam structure. I'm really fascinated about dam structures. There's something about them. Maybe it's because I'm an engineer myself and I'm in the construction space. And I get to be exposed to a diverse range of infrastructure projects because in geotechnical engineering, we almost work in any type of infrastructure projects because everything needs a foundation. So I think these guys did a great job in animating and explaining things in a more simpler way that most people can understand. I recommend you to go check out the original video. I will leave the link in the description down below. Thanks for watching. I'll catch you on the next one.